Seest thou what rage transports our adversaries, whom no bounds prescribed, nor bars of hell, nor yet the main abyss wide interrupt can hold? So bent they seem on desperate revenge, that shall redound upon their own rebellious heads.
In the waters of Dalobar, orbiting the star branches, life is ready to emerge. Welcome back to Nats Geo. In our last video, we established the aims of this series and sketched a brief outline of the branches system with its major celestial bodies. Now we focus our attention on Dalobar, the innermost planet. Like in the last video, I've pulled a word from the Webster's Poll Parrot Dictionary made expressly for George Rabalad of Alturas, California. Our word is redound, meaning to roll back, result. Definitions in this particular dictionary can be terse and at times archaic. Redound has additional meanings listed elsewhere. Nevertheless, these are the definitions which we'll be using. I've done another public domain search on Wikimedia Commons. This time, only 2 images match the prompt word. One comes from the wartime diary of British satirist Thomas Butler Gunn. The other lambasts the socio-political trends facing Great Britain in 1793. It quotes Paradise Lost by John Milton. On their face, these artifacts of imperial strife have little to do with today's topic. We'll keep them in mind and move on to our first clade. As in our world, radiation and thin atmosphere will compel Dalabar's organic life to find its first foothold underwater. Unlike our world, the first organisms will emerge far from the surface around thermal vents. The same tectonic plates pushing together in the east to form Dalabar's super tall mountain will roll back along a shelf in Dalabar's western oceans. That rollback will result in high volcanic activity, which will give a set of single-celled chemophytes the nutrients they need to power biological processes. These chemophytes will begin with a simple set of functions: clinging to the seabed, ingesting waterborne ions, and storing their energy. These chemophytes get their energy from environmental electrons, unlike the photons used by plants and other phototrophs on Earth. Clustered around the thermal vents, these single-celled organisms will begin to pile up, leaving some with limited access to the seabed and others with limited access to sediment. Under those conditions, some may make the leap toward colonial and then eukaryotic fusion. This first clade of multicellular life on Dalabar will function much like its predecessors on a larger scale. Some cells will specialize to anchor it into the rock, others will specialize into absorbing nutrients, filtering out waste, storing energy, and circulating to other parts. Each will contain genetic material to reproduce asexually. As the yups grow, buds will form and then snap off. Water will carry those buds a short distance away where they will anchor themselves and repeat the process. As the first yups proliferate, their narrow habitat will become crowded. When it does, competitive pressure will push them towards greater and greater specialization. Some may maximize verticality, evolving to digest more complex minerals from the vents and secreting the waste to form a rigid casing. Those yups will dig their anchors deeper into the rock for stability and extend multiple branch-like spokes to maximize surface area. Spokes will swell up with stored nutrients before splitting off from the hub to float to a new location. Powerful ocean currents may carry bulbs outside the range of their habitat. Most will die, but a few will adapt to free-floating life near the surface. Dalabar has solar energy aplenty for life forms able to harness it. Over the long timeline of early life, one drifting bud will make the switch. Its descendants will become the first Terops, with lightweight, floating entities that will blanket Dalabar's early oceans like phytoplankton on Earth. These Terops will be autotrophs, making their own food. Remember that chemophytes can be autotrophic too. Humans and other animals are heterotrophs, consuming other life forms for their organic compounds. As the surface waters become crowded, some Terops will adapt into heterotrophy. This will start as simple linking together for greater area. Over time, the heterotrophic Terops will shift towards absorbing whatever they latch onto using their enlarged central pores. They will have radial symmetry along a simple column with a varying number of segments. Some pores along their side will adapt to take in light, becoming rudimentary eyes. These Terops will enjoy a period of unchallenged dominance, but developments on the ocean floor will soon reach new heights. The maturing seabed ecosystem will lead another lineage of yups to develop heterotrophy. Their spokes will stretch out from the central hub, tapping directly into the yolk's pores and siphoning off a portion of their energy. These first uranoids will maintain anchors but lose the hardened casing and grow generally squatter to the ground. Detaching bulbs and dead cells drifting down from the surface will provide a diet for a new set of these uranoids. Anchor tendrils will reposition themselves around the top of these creatures to hook in passing food. The circulation channels, which distributed food to the base of the yolk's vertical hubs, will endow these tendrils with the most advanced musculature yet on Dalobar. These uranoids will sense motion and particulates using their tendrils and pores, respectively. Unlike their siphoning cousins, they will develop a single upper mouth. Some will latch onto rigid yolk casings rather than the ocean floor itself. Others will take the tendril musculature to its logical conclusion. Uranoids will vary drastically in size. Some will siphon energy from dozens of yolks at once, others will evolve to pluck bulbs off a single hub. At the extreme end, some may perch on individual spokes, pinching away one bit at a time. Some of these may be carried up towards the surface when their bulbs detach. Relative dexterity will give these hitchhikers a huge advantage over the drops occupying surface predatory niches. They will therefore undergo evolutionary radiation and become Dalabar's first truly motile life forms. Unlike sessile organisms on the seabed which anchor themselves in place, or drops which float on the whims of the tide, motile Retsbu can propel themselves against the current. This motion will encourage cephalization, a consistent trend among animals on Earth whereby mouths, brains, and sensory organs concentrate at the front of an organism to form a head. Despite that, Retsbu will retain traces of their radial heritage in the form of eyes, whiskers, and fins banded around their length. Some will evolve wide mouths and perhaps even tongues to scoop up the drifting drops. Others will evolve to hunt their large motile cousins. Hooked tendrils will sharpen into pincer-like structures around the mouth. Skin stretched between their spokes will allow them to rapidly displace bursts of water in a deadly charge. While these pincer-mouthed Retsbu won't grow quite as large as their scooping counterparts, they will be the apex predators of Dalabar's early oceans. With these 4 clades, we've come to the end of the material I'd hoped to cover on this month's episode. Next month, we'll explore how some of these life forms make the difficult transition onto land. Special thanks to Kella for the use of their microphone. My audio would have been worse without it. Thanks as well to everyone who contributed art for this month's episode. Reach out through the website for briefings on the next installment. Lastly, thank you for watching. I'll see you again next time.